although most of you probably already know what probability is, and you have already probably applied it in your daily life, such as the raining and umbrella example that I just gave you, we have to now describe it formally in mathematical terms. So this chapter is trying to do that, and it's called Elements of Probability. These are the references that were used in the preparation of this course. So I'm going to start with this graph that I had already shown you previously. If you recall, this is the process of statistical inference. So when you're studying a population, obviously you cannot study it in its entirety. So you take a sample from it. From the sample, you then study these individuals. You measure certain aspects, certain properties, certain statistics. Then you use these statistics to take a generalized an educated guess, a generalized idea about the entire population itself. In order to do that last process, to generalize, the probability theory can give you a basis for the science of statistical inference. So if this, then what? If I have this data, then what can I conclude from it? So in order for us to go about it in a more structured way, I have tried to divide the lecture into 6 main points. So we have the sample space and events. We have complements, combinations, and algebra of events, axioms of probability, conditional probability, the Bayesian rule, and independent events. So my target today is to try to cover the first 4, if possible. If not, maybe the first 3. Then we can finish off the remaining parts next week. First, I'll talk about sample space and events. So we have already actually talked about this in the very first lecture, Introduction to Statistics and Probability. Because if you recall, this is these words, the sample space and events, were some key concepts that I asked you to review because they are important, because we are going to use them over and over again in our course. So the correct definition, or the formal definition, would be the sample space is the set of all possible outcomes of an experiment. So don't be too afraid of the word experiment in this context, because I'm not talking about like a sciencey, like a real academic, a real sciencey experiment. But in this case, the definition of experiment that we use in this context is any procedure or any possibility for which more than one outcome is possible. Case in point, if it will rain or not today. There are 2 possible outcomes to that particular question. It could rain and it could not. So this is our experiment in this context, raining, the event of it raining or not. Another example, maybe this is quite standard. You probably know that a lot of probability problems are based on these, on coins and so forth. So if the experiment consists of tossing a coin, like heads and tails, then my sample space would be head and tail. Note that I'm writing S equals, the sample space equals, and I'm using the curly brackets. This is the formal the formal set notation, and please recall from your discrete mathematics course. And the second experiment, for example, if it consists of a race among 6 horses, so I have 6 horses, the results of the race could be, or the sample space would be, all orderings of 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, 1, 3, 2, 4, 5, 6, and so forth. And if our experiment is about today being rainy or not, that means our sample space would be rain or shine. Don't forget that if you were to be asked to write the sample space in a question, you need to use the correct set notation when you are denoting the sample space. So next, when we're talking about the sample space, a lot of the time, games of chance are a really good way to illustrate this concept, because these things are all experiments, because we never know what's going to happen. So if you remember, if you have a die, or the sample space would be 1, 2, 3, 4, 5, 6, because there are 6 sides to a die. But if I have 2 dice, then the sample space, you probably are going to see this many times throughout the course, is the sample space of rolling 2 die is the combination of the 2 sides of each die. So in this case, this one, 1, 1, it means that the first die gives us number 1 and the second die gives us number 1. This one is the first die giving us number 1 and the second one giving us number 2, and so forth. And if I wanted to write this correctly as a sample space, I would need to write it as follows: 1, 2, and so forth until 6. So now, since we've already established our sample space, aka everything that could happen, now we need to consider what actually does happen. So, like for example, I'm talking about a certain event, like today. Is it raining today? Is it raining at any of your houses? Let me check real quick. The event, or what actually happens, is that it's not raining. So if I say that a certain outcome of the experiment is contained in E, I say that E has occurred. So in the case of the rain or shine, like the example that I'm talking about just now about the raining. So the subset of the sample space, the event that could happen, we have 2. We have the event that it's raining and the event that it's not raining. But if the actual outcome is contained in that, that means that's what actually happened. Like, for example, the event that an even score is recorded on a roll of die, those are the events that would fulfill this description. Say here. So when I'm talking about the event that an even score comes up, if it comes up 2, that fulfills it, 4, it fulfills it, and 6, it fulfills it. The event that we get head on the toss of coin, E equals head, and the event that today is not raining, as it actually is not raining, then I could say E equals shine. And so. Okay. You've noticed that we have been using these curly brackets for the last couple of slides. You also notice here that we have been using these languages, the language that we've been using, sets, subsets, and so forth. Does that remind you of anything? You probably have already learned about all of these, set theory, in your previous courses. Short break, because we are going to review these concepts shortly. My clock is 14:03. I'm going to give you guys around 2 minutes now for a short break to remember these concepts. So when we're talking about set theory, obviously you probably remember the Venn diagram. You don't really need much. So when we're talking about the Venn diagram, we have something like this. That is my Venn diagram. If you're talking about set theory, I believe you give this entire box is called the universe. Please correct me if I'm wrong. In Indonesian, it would be semesta, or like everything that could happen, every possible scenario. And in the context of probability, then, this is our sample space. This is the space that represents every single thing that could happen. For easier context, let's consider the dice. So I know that if I have one single dice, what could happen, any possible outcome that could happen is that I could obtain any of these numbers. I could obtain a 1, I could obtain a 2, and so forth until I could obtain a 6. So here, in this context, I would like to consider, the event in which I obtained an even number. Or if I were to write it correctly in mathematical formula, in a mathematical notation, I would write it as follows. So these are the events 2, 4, 6 that could happen for it to fulfill this criteria that I set. Whereas here on top is all of the possible outcomes. So if I'm trying to symbolize my E, even numbers here, I could write it as follows, right? This is my E. Until here, this is just a review, right? Okay, so this is my S and this is my E. And I would like to make it clear. So this is, color. Can I have a gray ink color? No, I cannot. Okay, I'll just use black. So I'll shade it just to make it clear. This is my event space. So when we're going over these concepts here, does anyone care to remind me where would the complement be of my E in this context? Here it's E complement. Anyone? There's a chat. Was that Johannes? Okay, sorry,
Yeah.
Johannes. Harold already wrote in the chat box. Next time, okay? So
Yes,
Harold says in the chat box, other events outside of E. Exactly. Or in other words, right here, all of these other areas. Am I correct, Harold? Hopefully I'm correct. So if you recall the set theory, this is the complement. I'm trying to make it color-coded, okay? So it's yellow, it's orange. So here, that's the complement. And doesn't that make sense? Because when I'm talking about sets as well as outcomes of an experiment, when I'm talking about E numbers, which would be 1, 3, and 5, which is everything else aside from 2, 4, 6. And since everything else, every possible outcome is represented by the entire box, obviously, if this is the the even numbers, then the odd number should be everything else. Okay, that makes sense, right? Next, say I have another event that I want to consider. Say I want to consider a second event, which is, let's say, prime numbers, for example. So remind me, don't let me make a fool out of myself. Prime numbers, 1, 2, 3, and 5. Okay, anyone correct me if I'm wrong, okay? I believe it's correct. 1, 2, 3, and 5. So in this case, I'm going to annotate using the color green. So the second event, okay, is someone correcting me? 1 is not a prime. Okay, see? Thank you very much. 1 is not a prime. Let's erase that then. Here's my pen. Thank you for the correction. So here, I'm going to denote this second event as F. In this case, we have that is F, and it contains 2, 3, and 5. Note that I put it intersecting E because we have an intersection here. So here we already have a hint of this one. So when I say a union of E and F, thus here, up into here, like that. And if I were to write it mathematically, it would be EF 2, 3, 4, 5, 6. Please correct me if I get anything wrong. And if I have intersection, that means I would write it as follows. Anyone? So E intersecting F would be, help. Oops, there's a chat. 2, exactly. Good on Johannes. Don't forget your set notation. So here we have 2 here. Oops. That is somewhere in here. So let's put yellow notation here just to make sure we understood. It's somewhere in here. That's the intersection. And oops. And that is the union. Okay. So now I would like to, I have another event, final event. I have the event G. Okay. And this is the event in which the, what do you call it? The die will show me the number of girls in the 2020 international class cohort. Please correct me. If I recall, there were 3 of you. Am I right? Was it 3 or 2? I have to look at the participant list. 3, right? We have Anna, we have Indira, and we have Audi, if I'm correct. Please correct me if I'm wrong. I think there's 3. Yes, 3, right? So if I'm talking about this last event, in the case, there are 3 students, but there are only 2 actually today, right? I think Audi actually told me that she's unable to attend today. So today there's only 2 of you in class. So in this case, we have only 2. This is the event in which the dice shows the number of females in class. Okay. So if you see here, when I'm talking about subsets, we can also say that G is a subset of E. Here, that's a subset. So here I'm going to write G somewhere here. Like, for example, this is my G, that's my G. And I can say that G is a subset of E. Have any of you seen this symbol before? That one. What's the difference between this symbol and that symbol? This is what we're going to look at when we're talking about subsets and proper subsets. So up until now, I showed my very messy handwriting here. So let's go over the concepts once again in maybe a little better visualization. Here is the complement of E, which is everything outside of your event. Here, we're talking about the union of E and F. So when we're talking about 2 different events that happens. Next, we have the intersection of E and F, which is the subset in which both of them come up in E as well as in F. So the shaded region here, we already drew that. However, there are 2 things that you need to know. If you have 2 different events, E and F, that are like this, then you can also say that EF or EF is an empty set, which can be symbolized with empty set like this or empty set like that. Then you can see that say that these events are mutually exclusive. So in the sample that we had previously here, the event of the dice giving us an even number and the event of the dice giving us an odd number, these 2 events are mutually exclusive. However, when I'm considering E and F, E being giving us, the dice is giving us an even number, and F, the dice is giving us a prime number, these two events are not mutually exclusive. So this is there are these two special events in the case of intersection. So lastly, when we're talking about subset and proper subset, we have these two symbols. So if you recall, the subset and a proper subset are different in the sense that I can write it like this. So the equal, like the exact same set can be noted as the subset. However, it cannot be written as a proper subset. So when I'm saying subset using this symbol, that means it could be equal as well. But if it is a proper subset, then it cannot be an equal set. It has to be a proper subset or less amount of members than the bigger set. And based on these properties, we can say that E, and if E is a subset of F and F is a subset of E, we can say as well that E is equal to F. Don't give up yet. We still have some mathematics here. You probably have already covered this in your previous course of discrete mathematics. Sadly, we will not go into this in detail in statistic course because it is assumed that you already know these laws. So it may be necessary for you to figure out the algebra of a combination of events, and these laws can help you out in order to define or denote these events correctly using the correct set notation. Once again, we are going to take a pause. So now that we have our events, we want to know what's the probability of that event actually happening. Okay, so this is the part where we're actually going to try to answer the probability of these questions. So will it rain or not today? We already talked about that. Like, will the amount of gas in my car allow me to drive from UI to PIM today? Will it be enough? Should I take that freelance job? Is UI library crowded today? So the basis of me answering these questions will be my attempt to measure certain probabilities. Like, for example, if it's raining or not today, I'll have to consider various things in order for me to get a good idea in my head. Oh, there is a 0.x% chance, there's a 0.x probability or X% probability that it will rain. Oh, the gas in my car, there is a 90% probability that I would be able to make it to PIM from UI today, and so on and so forth. So the definition of probability is based on this empirical fact. If I repeat an experiment enough times, if I do it over and over again enough times, the proportion of times in which an event occurs will approach some constant value. So if I'm talking about the amount of gas in my car, is it enough for me to drive from Depok to Pondok Indah today? So if I do that over and over again, if I drive from UI to PIM every single day, enough times, eventually the proportion of times in which my gas is sufficient will approach a certain number. And that is the probability. There's a certain number of times among all of the times I do that, a proportion or a fraction of times in which it will work, it will happen, it will be okay. So this proportion we call the probability of the event, which we write in correct notation. We write it as PE as follows. Yes, like that. And what it means is that how likely will this event occur? So if I were to say PE equals 0.9, and I would say that PF is 0.2, you probably can get some conclusions from these values only. For example, the probability that E is happening, it's more probable than F happening. If this probability is rain, then I should probably bring my umbrella today. If this probability is the probability of me getting the lottery, maybe I shouldn't spend my time or my money on a lottery ticket and so forth. So based on these logic concepts, we have some axioms. What's an axiom? It's a rule sorry, I'm trying to do that. Okay. Or some theories that we can hold on to. We can say confidently that these things will usually or always hold. First is the first axiom. We say that the value of a probability of an event will be between 0 and 1. We already covered this in the first course of the introduction. That means that we can denote the probability in two ways. I can use percentage, because percentage is just 80 over 100, right? So it is between 0 and 1. Or I can say 0.9 and so forth. So there are two ways that it can be denoted, either in a percentage or a decimal. And note that the probability of the sample space is 1, which means that the sum of every event should equal to 1. And lastly, so here, if I say that for mutually exclusive, remember what that means. It means that there are no intersecting outcomes. So from two different mutually exclusive events, E1, E2, then the sum of the probabilities of each event would be a sum of the individual probabilities. So if I know that E and F are mutually exclusive, and I know that PE is 0.2, PF is 0.5, I can say that PEF will be 0.7 because it is the sum of the individual probabilities. If and only if the events are mutually exclusive. If the events are not mutually exclusive, aka there is an intersection between them, then this property does not hold. I cannot just sum it up like this if there are intersections. So from this page, we already can answer two questions on your pre-test, which is this statement correct? PE equals 2. Anyone? Do you think that's correct? PE equals 2. Is this a good statement? Would this work? Anyone? Chat box? Johanna says no. No, you cannot say this. This is not correct. You cannot say that a probability of an event is 2 because we already said that the probability of any event must fall between the values of 0 and 1. Next is, if I know that the probability of E is 0.2. Wait, I don't actually remember if this is in your quiz, sorry. But and we have PF, and I know that the probability is a 0.8. Does that mean that the probability of EF must equal to 1? The answer is no. This is also false because we don't know if E and F are mutually exclusive. If they are mutually exclusive, then yes, I can sum it up into 1. But if they are not mutually exclusive, there must be an intersection between them, and the sum of both of these events will not be equal to the sum of their individual probabilities. So based on these axioms, we then have an additional propositions. We have two different propositions that come up. In this case, when I'm considering a certain event, E, recall that this is E, this is E inside and this is E complement outside. I know that PE complement will be 1 minus PE because don't forget that the of the entire sample space equals to 1. So we can do 1 minus PE. The second is when I have two different propositions. Two different events, E and F. The probability of E and F is the sum of their individual probabilities minus the intersection of their probabilities. So in the case of mutually exclusive events, the Venn diagram would look something like that. It would be E and F, and thus it would be PE plus PF minus the P of an empty set, which is then canceled out, and that what's bring us to the sum of these events eventually. Okay. Oops, sorry. Okay. It changes, right? There is a random animation there. I apologize. Okay, and lastly, we know that if I have an experiment with the entire sample space consisting of all of these different outcomes, outcome 1, outcome 2, and so forth, the probability of every single outcome is denoted by PO, and it satisfies these two criteria. Each individual probability will be between 0 and 1, and the sum of every single outcome will be 1. Note that here, this is a probability of an outcome and not of an event. Recall that an event can consist of more than one outcome. Like, for example, the event of even numbers, we have more than one outcome. We have 3 outcomes inside of it. And finally, these things also are valid as a result of the previous propositions and axioms. So we know that the probability of an empty set is 0. The probability of the complements can be computed based on the probability of the sample space. This is the probability of the union of 2 events, as well as the subsets. If A is a proper subset of B, then the probability of A must be less than the probability of B. Any questions? If there are no questions, we're going to move on to an exercise. I'm going to give you some time to go over this exercise in your head before we start doing it together. Okay, so now we also have a second example. We have a total of 28% of American males smoke cigarettes and so forth. I invite you to try these examples out on your own time because we don't have time to cover all of them in class. Go ahead and check your modules on Scale to find the key as well. Based on the logic that we have up until now, this makes a lot of sense. We already defined the sample space. We have 6 possibilities. Then we also define the event that we're talking about, which is that the phase will equal 6. Then we compute the probability by writing. What is this? Let's define this. This is the number of outcomes that is included in the event. This is the number of outcomes that is included in the sample space. Makes a lot of sense. That is how we are supposed to compute it. But please keep in mind that actually this computation 1/6 is based on a very large assumption. In theory, actually, we cannot guarantee that every single time I have a die, I throw it, it will come up a probability of 6. The probability would be 1/6. We actually are only able to compute that on this very large assumption We assume that it is a fair die. We assume that the die is not tampered with. We assume that the die is a normal, actually, die. And we assume that all possible outcomes are equally likely to occur. So among these options, 1, 2, 3, 4, 5, and 6, we have to assume that every single event is equally likely. Then yes, the explanation that Akil gave us and the answer that Arya gave us is correct. The probability will be equal to 1/6. This is an assumption that we will be using throughout our course. However, I would like you to remember that this is not, it's not a given. It is used in probability theory in order for us to be able to describe all of these events. However, in real life, this is a large assumption that we put in place in order to compute it easily. So based on this assumption, then it's natural to assume that each point in sample space is equally likely to occur and so forth. And thus we can compute PE, or the probability of that event happening. In the previous slide, it was the probability of the event that number 6 comes up, by computing the number of members in E and N. N is the number of numbers in the whole sample space. So if I assume a fair dice, so this is implicit when I say it's a fair dice, I assume that each outcome is equally likely, The event in which an even score is recorded on a roll of die, so I can write this event as even, 2, 4, 6. For a fair die, the probability is then as follows. Because the probability of it coming out 2 should be 1/6, coming out 4, 1/6, 1/6, and thus the total is 3/6 or half. If I consider 2 die, then the event of the sum of scores of the 2 die equal to 6, aka the event is 1, 5, 2, 4, because the sum of this is 6, sum of 6. Then for the fair die, the probability would be this event is 1/636, this event is 1/36, and it will equal to 5/36, because obviously a combination of 2 die, we have a total sample space of 36. And if we assume that all outcomes are considered equally likely, then what's the probability that both dies have even scores? So here, even scores in both dies. This will fulfill it, this will fulfill it, and so forth. Note that the event A is when it's obtained on the first die and B is on the second die. But in total, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 events. And thus this probability of P and B should be around 9/36. Am I right? Let's see. Yes, 9/36, or we can simplify that into 1/4. So here, what about this case? When the probability has at least one die has an even score. In that case, we have PA union P. We can then see that there are 1, 2, 3, 4, and so forth. I don't remember how many. Let's check the key. And the key says there are 27 events that fulfill this criteria, and thus we can compute the probability as follows. Another example is that in this case, I know that a family has 3 children. Find the probability that 2 of the 3 children are girls. Big assumption. Suppose that all outcomes or all combinations are considered equally likely. In that case, we have all possible combinations of boy and girl of 3 different children. There are 8 total outcomes. So each probability is 1/8 because we assume that each outcome is equally likely. So the event that we are trying to compute, that we're trying to consider, is that the probability that 2 of the 3 children are girls. So among all of these 8 combinations, these outcomes are the ones that fulfill 2 out of 3 are girls. And thus, in total, we can compute the probability of this event as follows: 3 out of 8 in the sense, in 2 ways. I can compute each event. This is 0.125, and I times it by 3. Or I can just compute how many outcomes come up in the event, which is 3, and how many outcomes come up in the sample space, which is 8. And thus I get 3/8. Short pause. I have 2 questions for you to think about in this pause. So first is, okay, I get this assumption that we need to use in computing. Are there any questions about the concept itself? That's the first thing. The second is, although you may understand, don't you think it's a really big job if I actually have to write down all possible outcomes ever? Here, in this particular case, I only have 3 children that I need to consider. What if I am considering a class of 100 students? Obviously, it is not feasible for me to actually write down all possible combinations of 100 students that are female or male. So what solutions do you have? Once again, 2-minute short break to digest and think about the next points. So instead of us manually writing down or ordering all of the possible combination of events, we can use these tools to help us. Product rule, permutation, combination, circular permutation, ring permutation. Product rule first. Let's go. If I have R experiments, or in this case, maybe R possible events that could happen, and every single experiment has K1 possibilities, the second one has K2 and so forth, then there's a total of K1 times K2 times K3 and so forth events. So this is the product rule. And as you can see, it's just a product, which is multiply, multiply, multiply. So for example, how many possible outcomes would happen if we toss a coin? Heads and tails. And we subsequently roll a die. 4, 5, 6. Note that here it says subsequently. That means it goes 1 and then you do the number. So that would the second one, sorry. So that would fulfill the criteria of a sequence of events. So in this case, we know that the first K is 2, the second K is 6. And thus we know that there should be a total of 12 possible outcomes. We can also use a more complex ways of counting the possible outcomes by permutation and combination. So the main difference between these two is in permutation, you consider the specific order, and in combination, you do not need to consider the specific order. So for example, if I were to make a group, so I would like to make the group for the group assignment at the end of this semester. It's just an example. You can make your own groups, but for example, if I were to make the groups and I wanted to get a group of 3 from the students in this class, but I want to ensure that there is at least 1 girl. So in this case, I could use combination because it doesn't matter who I select first. So I could select the first one, I select Indira, and then I select Leonard, and then I select Nicholas, for example. It doesn't really matter if I select Nicholas first, and then Leonard, and then Indira, or if I select Leonard first, and then Nicholas, and then Indira. All these things are the same to me because in the end, I come up with a group of 3 people. It doesn't matter who I choose first. In that case, I can use combination, for example. But if another case was if I wanted to set up the order of a relay race. So international class is going to go and compete in a relay race, sorry. And I wanted to take a group of 3 people. So in this case, it would matter if I chose Akil first and then choosing Zuhri and then choosing Johannes. It would matter because whoever I choose first will start first in the race. So in this case, I need to use permutation. Obviously, I'm not going to go into that much detail because you probably already covered this, but I do acknowledge the confusion in this. So perhaps you should go over these concepts once again and find some exercises. There are some exercises as well at the end of this module that you can try out in order to figure out which combination or permutation are you supposed to use in that particular case. For example, PIN number. If I wanted you to see the possibilities of my bank PIN number, then it would be permutation because it matters which number I press it first, and so forth. So here, when I'm talking about permutation and combination, I'm assuming a linear combination. So if I'm talking about PIN number, then this could be any number between 1 and 9. This can also be another 1 and 9. And it is a line. So I have 6 digits and that's it. But what if I'm talking about a structure that's not linear in the sense of a circle and ring permutation? In the sense of if we had a wedding these days, right? And I would like to seat my guest at a circular table, then I could write it down as it would matter, like for example, where I put it, because not only is it linear, I also have a relation between the last and first element. And thus, in order for me to get this arrangement of n objects, I can also compute it using this equation here, as well as if I had more criteria, I can also consider the ring permutation. And it means that I don't care if it goes counterwise or clockwise. If it's the same order, like ABC this way or ABC the other way, I assume it's the same thing. And thus I divide it by 2 because the 2 different clockwise and counterclockwise directions don't matter to me. So I do recall that there is a good video out there that explains circular permutation very well. I'm going to go and look for it so I can either put it on Scalia or we can watch it together in class right now. But I would like to invite you to look at this example as an exercise as to determining what type of combination or permutation or ring permutation or simply product rule do you need to use to solve this question. So I'm going to leave you on this example on the screen while I look for that video. Please try to solve this example, and we're going to solve it together in about maybe 3 minutes, 3-4 minutes while I look for that video.